So as we said before then, if you're looking at a general data set, there's really two basic questions that you can ask: location and dispersion or spread. So if you look at location, which is the top arrow, what I'm thinking here based on the sort of technical term location is where does a typical observation live? What's my best guess as to what a future observation from the sample will be? Okay, and then alongside that you want some sort of measure of how far spread out the data set is. So technical term here would be dispersion or spread, and this is what things like the variance or the standard deviation or the interquartile range are measuring. So one thing that is sort of not always easy to reconcile is that you're given these formulae for the variance and standard deviation. It's not necessarily clear what these things mean. What they're really trying to measure is dispersion or spread. How far spread out is your data set? Okay, so there is a subtlety here in terms of statistics, not just mathematics. So location measures your sort of best guess of where a future observation will be, and dispersion or spread measures how far away you're likely to be from that value. Okay, the location is your best guess. The dispersion or spread is a sort of associated margin for error. And if you're looking at things in the right way, you want both sides of that in statistics. I wanted also to give a quick note on skewness and kurtosis. So if you look at the previous slide, you'll note that that is symmetric. So skewness refers to a situation where, in contrast, you have asymmetry. And another important concept is a concept of kurtosis. This is the sort of propensity for extreme values. So what can happen in finance is you get extreme outlying observations and relatively high probabilities of extreme events. Okay, and both skewness and kurtosis therefore mark important deviations from the classical picture on the previous slide. So these are important, especially for finance, and there are a number of popular books on this theme by Nicholas Taleb that are worth a read. Methods involving skewness and kurtosis tend to be more difficult to apply and hence are inherently specialist, so rightly or wrongly tend to ignore these on a sort of introductory course like this one. And then there's this important disclaimer: so skewness and kurtosis will be of only background importance in this introductory course, but will often be extremely important in financial problems in the real world. Okay, this matters because you might get important differences between, say, gains and losses, and also with kurtosis, you have high probability of extreme events. So the mean is the prototypical weighted average and is probably the classical data summary that you will be familiar with from high school maths. So what you do to calculate the mean is you just add up all the observations and divide by the number of observations in the sample. And so we've got this sort of numerical example here. So if you've got data in between the brackets, and just to calculate the mean, what you would do is add up all the data, divide by the 5 observations there are in the sample, and that will give you the mean. So the mean is just intended to give a sort of measure of what a typical observation might look like. Usually in practice you calculate this using something like Excel or another proper software package, although it's important just to sort of give you the hand calculation there. One thing I wanted to say on this, however, is that if you're using Excel to calculate the mean, there's a slight quirk in that the function you need in Excel to calculate the mean is average rather than the mean. Okay, other summaries like the median and the mode are more logically named by Excel, but in Excel, if you want to calculate the mean, then it turns out that the function you need to actually do this is the function average. Median is another data summary measure of location, so it gives you an indication of where a typical observation might live. Now it's sort of implicit in the name, but I've wrote it explicitly there on the slide, that the median is the midpoint of the ordered data. So if you phrase it like that, this indicates a slight difference that you have depending on whether your sample contains an even number of observations or an odd number of observations. Okay, and why did we bother with the median? Well, it's often thought the median might be a better summary of financial data than the mean, precisely because it will be less affected by extreme values. So in order to calculate the median, what you need is the n+1/2 ordered data point. So if you've got an odd number of observations, the median is just literally the middle data point once you place everything in size order. And if you've instead got an even number of observations, then what happens is that the median is the average of the two middle data points. Okay, so again, probably use Excel or a computer package to calculate the median in practice. There's a slight quirk if you're calculating this by hand, depending on whether you've got an even or an odd number of observations. So a couple of numerical examples then. So if you're asked to find the median of this sample, is order the data from smallest to largest, what we would do is calculate the point in size order, which would be this number 10. So the median would be this number 10. You've now got 6 observations in your sample. This gives an extra addition. So put them in side order again, and then you now want the 3.5 data point. So what you would do is the third observation and the fourth observation and divide by 2. So in this case, this gives you the value of 11.5. So perhaps I should have chosen a slightly more cunning example, but what happens here is that if you add in the extra observation, the median doesn't change by very much, although the mean would change by quite a lot. Okay, and this gives you an example, hopefully if you squint a bit, that the median is more robust to outlying or extreme values that might occur in the data sample. So it's a little bit rubbish in comparison, but I have included the mode as an alternative summary of location for a general data set. So the idea is that the mode is the most commonly observed value, but in practice the median and the mean are probably better summaries of any data set. So this isn't just sort of my opinion, there's a sort of slight complication in that the mode may not always exist, unlike the mean and the median. Okay, so we've got some numerical example data in between the brackets, and what you would do is just do some sort of tally chart, and the mode would be the most common value, in this case 18. Okay, now depending on what your data set looks like, it's not necessarily guaranteed that 18 would be a sensible summary for the data. Also, if you've got two numbers that both occur equally common, and these are jointly the most common in the sample, then the mode doesn't exist. Okay, so it's not guaranteed, depending on the vagaries of your data set, that the mode will be a sensible summary of that data, and the mean and the median would be generally better summaries. I wanted to sort of talk a little bit about computation in Excel. So there is a slight quirk in how this is done, in that the function you need to calculate the mean is actually average, and then happily Excel is a bit more literal for the other two measures. So if you want to calculate the median, then the Excel function you need is median, and if you want to calculate the mode, the Excel function you need is mode.sngl. So SNGL just refers to the single most common value. So suppose you have data in cells A1 to A10 and you want to calculate the mean. So what you would do is click on the insert formula icon FX, choose a category statistical, select average, press OK, then put the cells that your data is in the box entitled number 1, and it should calculate the mean for you. and then the median and the mode should be calculated in exactly the same way, except for the median, where you've got average, you would instead need the function median, and then for the mode, where it says average in point number 3, you would instead need to put in the function mode.sngl. Okay, so it's a bit hard for me to sort of go through the examples in these recorded lectures, but I will put an Excel example up on the canvas. So there is a rule of thumb that is often used in business mathematics books and in business mathematics lecture notes. This is not strictly technically correct, so there will be mathematicians out there that would sort of want to take a sniper rifle to me at this point for sort of mentioning this, but the rule of thumb is that the mean greater than the median suggests that the sample is positively skewed. If the mean is less than the median, then this suggests that the sample is negatively skewed. So this isn't strictly correct, okay, but it is often thought that if the mean is bigger than the median, then your sample is positively skewed. If the mean is less than the median, then it is negatively skewed. And if you had something that was symmetric, you would have that the mean was equal to the median. However, if the distribution is not symmetric, then this won't occur. Also, if the mean is equal to the median, this does not necessarily imply that the thing is symmetric. So, loosely speaking, if the mean is bigger than the median, it's positively skewed. Mean is less than the median, it's negatively skewed. That's the reason for the terminology, but this isn't strictly technically correct. Again, I wanted to sort of try and talk about this mental picture for a given data set. So the top arrow location, so this gives a summary of where the typical observation lives. So if you took another observation from the population in your sample, what would your best guess of that value be? And then dispersion or spread gives you an indication of how far spread out the data set is. So if you took an extra sample, how far would you likely be away from your best underlying guess? Okay, so the location is your best underlying guess, and the dispersion or spread is your sort of margin for error. Now, the reason I sort of try to phrase it like this, partly I like pictures whenever I'm talking about mathematics, but the important thing to say as well is that if you're given the formula for the variance or standard deviation, it's not necessarily clear what this thing is physically that you're asked to calculate. It is a measure of dispersion or spread. Okay, so this is a sort of useful mental picture to have in mind with any statistics and any data analysis. What's your best guess? The location. How far spread out are you likely to be away from that? The dispersion or spread. So for dispersion then, what you want to measure is how far spread out the data is, and the most commonly used measures of this are the standard deviation or the variance. So these two are linked together, so the variance is the square of the standard deviation. Currently, if you want to calculate standard deviation, first get the variance and then take the square root. So there's some suggestion in sort of practical data sets that use of the standard deviation may be preferred. So for instance, if you're looking at weekly sales figures measured in units of a pound, so the standard deviation would also be measured in units of a pound, so it sort of shares something in common with the original data that you've collected, but in contrast the variance would be measured in units of pounds squared. Okay, so I don't want to sort of kill everybody with dimensional analysis, but it's sometimes thought that the standard deviation is more useful precisely because it's measured in the same units that the original data is collected in, and alongside that, because it retains the same units as the original data, it's often thought to be more convenient to communicate information about the spread or dispersion using the standard deviation than the variance, although these are in essence two sides of the same coin.